the Illinois Math Science Academy, and today we're going to be talking about P versus NP. So, what is P versus NP? P versus NP, or solved versus verified, is a major unsolved problem in computer science revolving around the equation P equal to NP, or if P is not equal to NP. What P versus NP is trying to show is if P, all problems that can be solved quickly, and NP, all problems that can be verified quickly, are actually in the same bubble if they're both equal. They're both equal. But before we can get to all of P versus NP, we first have to understand the concept of polynomial time. Polynomial time, which is best exemplified in an example. Imagine you have an unsorted list of numbers, and you want to write an algorithm to find the largest one. Let's call it the quicksort algorithm. The algorithm has to look at all the numbers in the list and keep a record of the largest number it's seen so far. So it only has to look at each entry once. The algorithm's execution time is thus directly proportional to the number of elements handling, which computer scientists designate n. Any problem that can be solved in n to the power of x time is called polynomial time. The inverse being any problem solved with exponential time, x to the n, where n is the number of variables in the problem. So, using this definition of polynomial time, P is a set of problems that can be solved in polynomial time. And NP is the set of problems that can be verified in polynomial time. Imagine a chess game. A computer can easily verify that yes, the king cannot move anywhere, so it's a checkmate. But can a computer achieve this checkmate? Think of all the factors the computer has to consider. Bishop to e5, knight to c6. After only 4 moves, there are over 300 billion objects to consider. Can a computer do all of this in polynomial time? Let's take a math problem to further simplify this. Does a subset of a set of these 6 numbers equal to 0? Yeah, the answer is yes. It's easily checked because these 3 numbers add up 0. You easily check with -2 plus -3 plus 5, which equals 0. But as per today, there is no computer algorithm that can solve this problem. That can get all the combinations of these 6 numbers and check if they equal 0. In a world where P is equal to NP, there would be one. So say we did find an algorithm that figures out that these 3 numbers are equal to 0, then we would know that P is equal to NP. But if no algorithm is ever found, then it's obvious that P is not equal to NP. Let's do one more problem for those of you that might be a little slow. Imagine a basketball game. As the ball shoots through the air on an arc off the point guard's wrist, a computer can easily check and tell us that the shot was the shortest and fastest way to get the ball in the net. That's NP. But now you imagine that the same computer has to compute the fastest and easiest shot, factoring in wind speed, spin on ball, velocity, and wind direction, plus many, many more variables. Can a computer calculate the trajectory of this shot, all in polynomial time? If so, then we have P equals to NP. So let's summarize. P is a set of problems that can be solved quickly in polynomial time. Right? So a computer trying to figure out the fastest way for a checkmate, or the fastest way to get a goal. While NP is a set of problems that can be quickly checked in polynomial time. Right? So is it a goal, or is it a checkmate? But why does P versus NP matter? Why does this problem affect us? And why is it? Okay, so imagine a traveling salesman that's very lazy. He wants to visit as many houses as he can to get the most money, but he also wants to end up back in his own house. To make things even more complicated, he wants to take the shortest route, not one step too many. Is it possible to calculate the shortest route that this salesman can take? You can find the shortest distance. This is a classic example of P versus NP, as the left is solving the problem with 7 houses, and the right is checking that the solution is right, or P versus NP. This is what we call an NP-complete problem. The NP-complete problem is where a given solution to a problem can be verified quickly, but there's no known efficient way to locate a solution in the first place. NP-complete problems mean that there is no fast solution to them, but they can be easily checked. The traveling salesman problem, as this is formally called, is the NP-complete problem. NP-complete problems are known to be some of the hardest problems known to mankind. If P is equal to NP, then solutions to this problem and all other NP-complete problems will pop up, solving some of the biggest mysteries known to mankind. Okay, so I know this is a lot of information, but here's some more that should simplify it up. If P is equal to NP, then that means all problems that can be checked quickly, that can be verified quickly, all of those problems are equal to the set of problems that can be solved quickly. So all of the NP-complete problems and some of the biggest mysteries our world has to offer. Because we know they can be checked quickly, we know they can be solved quickly. But if P is not equal to NP, then we know that all of these problems that can be checked quickly cannot be solved quickly. And that's the end of the line there. But you were probably asking at home, what do I have to do with this? Why should I be even interested in P versus NP? Here's why. There are 7 problems called the Millennium Problems. These are problems thought to be unsolvable. Until now, 6 of them remain unsolved. The Canadian Mathematics Institute puts up a $1 million prize called the Millennium Prize for anyone that can solve any one of these problems. P versus NP is often called the most wide open one of these problems. But if you somehow solved P versus NP, if you somehow got that P is equal to NP, then that would do much, much more than just win the Millennium Prize. If you got P equals to NP, you could take over the entire world. With that proof, you could create solutions to many, many unsolved mysteries on Earth. And beyond, and mysteries in space, mysteries all over the universe. But with that proof, you could also hack bank accounts. You could rob people of money. You could create world chaos and send the world to doom. Like a superhero film, the proof falls into the wrong hands, and havoc reigns all over the world. So be a superhero. Go save the day. Go get into math, into computer science, into anything you're passionate about. And go do something big. Go save the world. Because in the end, you, with math as your sidekick, might just be able to change the world for the better. But wait, there's more. I just like to thank Khan Academy and Breakthrough Challenge for giving me this opportunity. I love videos, I love math, so this is a great challenge for me. I also like to thank my parents. They've been with me the whole time. They supported me the whole time, my retakes from the camera and everything. Thank you guys are the best. I love you guys. I'd also like to thank my school, IMSA, for giving me this whiteboard to use, and also for giving me a great education. Without them, I don't know where I would be right now. But I'd also like to thank mathematicians, because those guys don't get any credit. They designed this marker, they designed this whiteboard, they designed this camera I'm shooting on, they designed YouTube, which you're watching this on. So thank you to them. And I just like to say, you guys are what make this world turn around its axis, what makes Earth rotate around the sun. You guys are the best. Without you guys, P versus NP wouldn't be anywhere. So thank you guys. You guys are the best. I'm going to dedicate this video to you guys. And as always, thanks for watching.